Hello, everyone, and thank you for attending the Solving Large-Scale Inverse Problem in Python with PyLops here at PyData Global 2020. Before we start, I'd like to thank the organizing committee of PyData for creating such a great opportunity for people to learn and explore new tools in Python, and I hope you'll enjoy coding with us for the next 2 hours. I'd like to start by just briefly guiding you through the main repository where we have stored all the different notebooks that we are going to go through today and some of the solutions. You can easily access this notebook and navigate through its content, and we will see later in more details what the different notebooks are about. Before we start, just a few words about the material that is covered here, how you are going to be able to run it yourself. We are suggesting two possible solutions. You can either use your local Python installation if you're familiar with creating a Conda or a virtual environment, and you can follow these instructions for further installing PyLops. Instead, you can also just use Google Colabs, and we provide links below. You can click and access directly the notebooks we are going to go through in Colab. In that case, just be aware that some libraries are missing, so we have a few blocks that you will need to run to install, for example, PyLops. And also, if you want to access the solutions, we have different links for notebooks that include solutions. Here are the three instructors today. My name is Matteo Ravasi. I work as a research scientist at Equinor. And we have also David Vargas and Ivan Vasconcelos from the University of Utrecht, which will guide you through the next notebooks later on. And as I already said, you can access our notebooks in three different ways. Directly from this link, you can see them in GitHub. You can, of course, clone or download the repository and access them locally. Or you can click this button and you will be sent directly into Colab. Before we start with the first notebook, I'll just like to give you a very brief overview of PyLops, which is the main library we are going to use today. And I highly recommend you, after the talk, if you start using PyLops for your own research, to go through the documentation and especially take a detailed look at the API of PyLops and all the different operators and solvers that we offer, because more often than probably you expect, you will see that some of the problems you want to solve can be easily solved by combining these operators without having to write any new operator or very limited amount of code other than using what we already provide. And let's see with the first introductory notebook if you can start to get familiar and start to use these operators to solve a few interesting problems. Before, just to make sure that we are all on the same page, I would like to have a very brief theoretical introduction to various concepts that will be recurring today. First of all, we are going to solve inverse problems, so we will see what is an inverse problem. We will also see why and in which circumstances you would like to use linear operators to solve inverse problems. And after this is clear, we will see how we can do that with PyLops, how we can set up our own linear operator from scratch. So you will see actually a bit more about the inner working of this library. And later how you can use those that are already available and combine them. Once again, as I already mentioned, here are three very useful links for you later on. The link of our GitHub repository where you will find all this material, and the main repository of the PyLops library and the reference documentation you have already seen. So let's start with some theory. I'm expecting you at least to have some basic understanding of linear algebra, and provided that you should be familiar if you look at this cartoon to see that generally we can write a problem, or in this case a linear problem, as follows. We have a vector y that belongs to a space of dimensionality n. We have a vector x that belongs to a different space or possibly different dimensionality. We will say of dimensionality m. And we have an operator a, which in our case is a linear operator, and in even simpler way is just a matrix of dimensionality n by m, which if we apply it to the vector x will bring us to the dimensionality of the vector y. We call this our forward model or forward operation. Conversely, we have something that is called the adjoint model or the adjoint operation, and you will see later why this is very important. And this can be simply written by taking the matrix and applying the adjoint, which means applying the transpose of the matrix. So we transpose the matrix. As you can see, we take this 3 by 2 matrix into a 2 by 3, and we put all the elements that we had on the columns of the rows and vice versa, and also we apply the complex conjugate. Now, if we apply this adjoint matrix to the vector y, we will get a vector x. So in its simplest form, I've been talking about A as a matrix, but you will see that in most cases, for real-life problems, this matrix will be too big to either be stored in memory and definitely to make operations with it, for example, to invert it. That's where the concept of linear operators comes in. And this is very simply stated as follows. A linear operator is just a pair of pieces of code, one that allows you to implement these operations. So taking a vector x as input applies the effect of the operator, the matrix A, and gives you a vector y. On the other end, taking the vector y, the adjoint piece of code will apply the adjoint operator and will give you a vector x. Finally, since we are interested to solve inverse problems, what we are most interested in is to invert the matrix A, or do that to the best of our capabilities, and apply it to the vector y to get an estimate of x. We will see how this is in practice mostly done by iterative solvers. And one of the advantages of iterative solvers is that they do not require to know each of the entries of the matrix or the operator A. They only need to know how you apply it in a forward and the adjoint mode. And that's where, as I already said, the concept of linear operator comes in. So we have now hopefully a basic understanding. And let's see what happens if we start going through one simple case, the Hadamard product, which we can also refer to as the element-wise multiplication. So the multiplication of two different vectors. And we will see how we can implement this straight using NumPy and using, for example, dense matrices to mimic this operation, and also how we can do that with PyLops. So to start, we're just going to import our usual libraries that we are going to need. Mostly in this case will be NumPy, SciPy, and PyLops, and actually some of the plotting. And let's have a look how we will write an element-wise multiplication. Element-wise multiplication can be very simply written in this compact form. We say we take each element of the vector x, multiply by each element of the vector d, and then we get the corresponding element of the vector y. If we were to see this as a matrix vector formulation, because this is what we want to do to be able to create a linear operator, and then possibly later chain this operation with other operations that will create maybe a more interesting forward modeling at the end, we see that the element-wise multiplication can be also seen as a diagonal matrix, which contains the elements of this vector d along the main diagonal, multiplied by the vector x. In this case, we can just, on pen and paper, perform the transpose of this matrix and the complex conjugate, and we get what we call the adjoint. So we see from pen and paper how we can implement the forward and the adjoint. Now, how are we going to do this in practice? Let's start assuming that we want to do this with dense matrices, for example, with using NumPy. So what we can do, we just say we have a vector diag that contains n elements, in this case from 0 to 9. We use the np-diag method of NumPy to take this vector inside a matrix of size 10 by 10 and place the vector along the main diagonal. And then we will have 0 everywhere else. Now we want to apply the forward. This is very easy because we can create a vector x. Let's, in this case, take a vector of 1s. We use np dot, pass the matrix and the vector, and we get the output y, which is the forward modeling operation. We want to also do this with the adjoint, and in this case it's very easy because we have access directly to the matrix, so we can simply transpose it with a dot t. We apply the complex conjugation, even though in this case it's not really needed because we are dealing with real numbers, and then we apply again np dot, now on the vector y. And this is what we get. So this is possible and easy. Why do we want to complicate our life and start to use linear operators? Well, before we even do that, let's try to look a bit at the limitations of this approach. Everything seems easy, but we have two limitations. The first, we are storing n-square numbers in our matrix, even though we know that the matrix is diagonal and only the elements along the diagonal are really the elements that we are interested in. Also, we are applying a dot product, which requires n-square multiplication and summations, but again, most of them will be with zeros. Of course, we can, in this case, use sparse matrices, like those, for example, that SciPy offers, and we will go a long way, but I'm asking you to just have some faith, and we're going to try to see how we can write this as a linear operator. And we will see later that this will bring benefit also over sparse matrices. We're going to do this using the notation of PyLops, so that you already get familiar with how we're going to implement, or we can implement an operator in PyLops. And this is done as follows. We just define a class, we give it a name, and we subclasses to the linear operator PyLops parent class, which is already pretty much taking inheritance from the SciPy linear operator, to which we have added some additional interesting methods and properties that you will see later on. To do the actual implementation, we only need to create and implement three different functions. The init function, like in any other class in Python. And then we have the so-called mathvec, underscore mathvec, and underscore rmathvec. Underscore mathvec performs a forward, underscore rmathvec performs the adjoint. And you will see that we are never going to call these directly. We will have some overload on some more mathematically nicely looking symbols. But this is what we need to implement. So how are we going to do it? In this case, it's very simple. We can just pass our diagonal vector, store it in our self diag. And then when it comes to the forward and the adjoint, we just apply it to the vector x with the star. And since both of them will be numpy arrays, this will be an element-wise multiplication. And when it comes to the adjoint, we can simply apply the complex conjugate, as you have seen in the equations above, and then we apply again the star. Two more things that we need to discuss before we move on are these two members of our class, the member shape and the member dtype. These two are always required. The first one, because we need to tell our code and eventually PyLops what is the size of the operator. We're not creating, remember, anymore a dense matrix, not even a sparse matrix in this case. So eventually the code is not aware of what is the size of our operator. And we need to tell it. In this case, this is very easy because this is just the length of the vector diag, both for the space, model space, and data space. And also we want to define a type, a D type, which we have set as default as float64. And this is because in some more complicated operators, for example, dealing with complex and real numbers, we want to make sure that within the mathvec and our mathvec pieces of code, we don't do some unwanted recasting of our input vectors and output vectors. Let's now run this cell and see how we can call this operator. We can simply say diagonal pass our diag numpy vector. And then if we print it, we see that this is a 10 by 10 diagonal operator, which has this D type. Now, are we going to apply it? We can do it with a forward. And as I already said before, we don't really need to access the underscore mathvec. We can use the star or alternatively also the @ symbol. And if we run this cell, we see we get the same result as before. But now we have not created a matrix. We have just defined a piece of code that applies this operation. Same for the adjoint. Now we have the .h that tells PyLops, or in this case, tells our implementation that we want to apply the adjoint. And only at the point where we have the star, we are really applying the adjoint. And this is the vector x h that looks like the exact same as before. So now it's time for the first exercise that you can go through yourself, and later on we can discuss in the Q&A session. What I'm asking to do is to make now this vector x and y much bigger and see how these two implementations compare. And as a bonus, if you want, you can also try using SciPy sparse matrices as a third way of implementing this diagonal or element-wise multiplication. Before we move on to a second operator, which is a bit more interesting and also a bit more challenging, so will hopefully give you a bit more understanding of the value and also how we implement linear operators in practice, we need to understand how to test our two pieces of code. We haven't, in this case, written our forward and the adjoint, but how do we really know that they are correct? How do we know that the forward and the adjoint are actually doing what their explicit matrix representation will do? And we know that if this is not the case, iterative solvers will generally diverge. We will see instabilities. And in some special lucky cases, we may still converge to solution, but we will see a slow convergence. Luckily, there is something called the dot test that allows us to test the validity of our two implementations. If you're familiar with linear algebra, you can see that if we start from this equation on the left, we have our operator A, and then we have two vectors, U and V, which are, we can just draw random vectors, one of dimensionality M and the other one of dimensionality N. If we now apply the forward, we get the vector of dimensionality N, and we then perform the dot product with the vector V and we get the scalar. Now let's use some simple linear algebra. We know that if we have the adjoint or the transpose of a product of a matrix of a vector, this can be written as swapping A and U and applying the adjoint to each of them. Later, we use the associative property of the dot product, same as the multiplication for scalars, and we can rewrite this equation in this form. So now we have UH that is applied to a vector that we have created as the application of the adjoint to a vector V. So what we see here is that we have now the possibility on the right to apply our adjoint piece of code, and on the left, the forward piece of code. And only if this equality is verified, we have guaranteed ourselves that what we have done is correct. So in PyLops, we can simply access these using the dot test method. We pass the operator, its dimensionality, and in this case, we are saying that we want it to be verbose. So we see some printing of the actual scalars that we get, and also that the dot test is passed. Now let's move to, as I said, something a bit more interesting, the first derivative. Well, let's imagine you have a signal, in this case a discretized vector that is representing a line with slope 1. We want to apply the first derivative, and we know that the derivative of y equal x is y equal 1. We also know that we can do this numerically if we have discretized this function as a vector x by taking each element of the vector at step I plus 1, also at step I minus 1, subtracting them and divided by 2 times the sampling. And this gives us the value of the vector y at location I. We can, assuming that delta is equal 1, we can simply write this again in our matrix vector formulation. And this is how the matrix will look like. And if we now, pen and paper, apply the adjoint, this is how the adjoint will look like. So now you can look at these two different matrices, and you can think about or start thinking about how you would implement this as a linear operator. As I said already before, you don't need to write a matrix. And in this case, I'm going to give you a couple of hints. You could use the slicing properties, for example, of NumPy, or you can see the forward and the adjoint as a pair of convolution and correlation with a small compact filter. I'm going to give you an exercise and asking you to implement it. But for now, we will just take the dense matrix implementation, which is creating, again, using NP-diag and doing a bit of small changes at the edges to allow implementing a first order forward and backward derivatives instead of the center derivative. And we're going to skip all the way to using directly the PyLops implementation. So we can just use PyLops dot first derivative, pass the length of the input vector, and we also use this edge equal true, which will do the same as the edges as we have done in the explicit matrix. We now run the dot test, and we see that the dot test will be passed. Now let's take a vector x that goes from -5 to 5 with step of 1. So analytically, this is a y equal x function like we have in the drawing above. And we know that if we apply the forward, either way as a dot product of the matrix d times the vector x, or using PyLops the op operator, forward operator, we should get a vector y that is a vector of 1. And that's what we get. Similarly, the adjoint, we have done it already before. We can just do np dot on the transpose. We know this matrix has only real numbers. Or we can use the dop.h of PyLops. And again, we get the same result. So we have proven that we can do this first order derivative in two different ways, with a dense matrix and also using the concept of linear operators. Once again, to understand the value of linear operators, I'm asking you to do these two exercises. The first one is the same as before. Let's just make the vectors bigger and see how these two implementations compare in terms of computational cost. And the second one is also to look at the actual memory footprint at the matrix D as well as the operator DO. And you will see, hopefully, if you get through these two exercises, the benefits of using linear operators for both of these two aspects of our implementation. But finally, what is more important is not really being able to perform forward at the adjoint. That's nice. But what we are generally interested in science is to solve the underlying inverse problem. So given a vector y, which has some observations that we can physically record, given our knowledge of a forward problem, in this case, the matrix D or the operator DO, how can we get an estimate of the vector x? And here we are comparing two different possible ways. Once we have an explicit matrix, we can use the LSTSQ method of SciPy, which will apply or solve the least square problem using a direct solver. And we can also use the backslash that we have implemented in PyLops as a shorthand, which we'll call SciPy sparse lineage LSQR solver, or depending on the size of the matrix, if the matrix is square, we'll call conjugate gradient. We run these two, and we see that we get the same result. Sorry, that went not where I was expecting. We see we get the same result, from -5 back to 5 for both the forward, the NumPy implementation and the PyLops implementation. Last but not least, before we move on to a second tutorial, is how can we chain operators? Let's try to make this problem a bit more interesting. We now say that we have a signal, for example, a step function, and our recording system is actually able to only record a smooth derivative of this input signal. So if we apply the derivative, we get a spike. If we smooth it, for example, with a filter of 5 samples, we get a smooth version or a small boxcar. How can we solve this problem? So far, we have seen all the time how we could implement PyLops operators one by one from scratch. But what is the, I would say, most powerful property of this library is that we can combine basic or core operators to create something a bit more interesting, like here, a smooth derivative. We can sum operator, multiply them. We can even put them into a chain, for example, stack them vertically or stack them horizontally, or put them into a block or block diagonal fashion. And let's see how we do that for this example. Again, we create just a vector x, which is pretty much mimicking the eviside function that we have seen above. We now perform the creation of the first derivative as we have done before, so this dop first derivative operator. And we also use PyLops smoothing 1D with a smoothing of 5 samples. We can now chain them with a star. You have seen already above that the star before was used to multiply an operator to an NumPy vector, and that would have triggered a forward operator. In this case, the star will just lazily combine them, chain them, tell PyLops that whenever we apply this operator op, the forward will have to apply this operator first, and then this on the result of the first operation. And the adjoint will do it the other way around with their adjoints. So we now create the data and again invert it. And here, I will not spend much time, but with PyLops, we have also access to more advanced solvers. For example, we can solve this by solving its normal equations with some Tikhonov regularization. And you will see later in the next tutorial much more on this. Let's run this cell, and you see how very quickly we get our data, and we get our model, which is inverted and is pretty much down to numerical precision, the same as the input model. And this gives us the end of the first tutorial. We have learned how to translate linear operator from pen and paper to computer code. We have seen how to write them from scratch, but also how it's important to be aware of all of the already available zoo of operators in PyLops and how they can be combined. And eventually you will see in the next tutorials how combining operator will bring you a long way.